Hello, I'm running a little late today, so hopefully I'm going to have this done before the bell rings. We're doing lesson 8-1, exponential functions. Okay, an exponential function is a function in the form of y equals ab to the x power. So this is the form of an exponential function. A has to be greater than 0, and A cannot be 0, B must be greater than 0, and cannot equal 1. So the base is a constant, and the exponent is a variable. So exponential functions are nonlinear. They don't have a constant rate of change like a linear function does, but they have a common ratio. So here's a linear function. Linear function, you notice here, they have a constant slope. It is the same slope, same rate of change. Whereas the exponential function, you notice it's not the same change. We have a little change here, and then it gets bigger and bigger because we're changing at a constant, this is a constant rate, this is a constant ratio. Okay, so let's see what that looks like when we do math. We're going to start with a word problem. The Richter scale measures the energy that an earthquake releases and assigns a magnitude to it. These orders of magnitude can be approximated by comparing them to the explosive power of TNT. Determine whether the set of data can be modeled by an exponential function. Well, as the order of magnitude increases, so if we go from 1 to 2, the amount of TNT that is approximately equal in magnitude increases from 0.6 tons to 6 tons. How do I go from 0.6 to 6? Well, I multiplied by 10. So that's an increase of a factor of 10. Let me see if it continues. If I look at magnitudes 2 and 3. So I'm increasing from 2 to 3 on the magnitude side. The amount of TNT that's equal in magnitude increases from 6 to 60. How do you get from 6 to 60? Well, you multiply by 10. It increases by a factor of 10. So because the amount of TNT increases by the same factor, given an equal change, so it was an equal change, they both increased once, equal change in magnitude, the data set can be modeled by an exponential function. So we're still looking at it's the same change, it's just a ratio instead of the exact same change. We're multiplying instead of adding. Okay, so try this check. See if you can figure out if it's representing an exponential function. In the 19th century, psychologist Herman, however you say that, created a formula to approximate how quickly people forget information over time. The approximate percentage of the newly learned information a person retains over time is shown in the table. Determine whether the set of data can be modeled by an exponential function. So let's look at 0 to 1. It's going down this time, so I might need a calculator. It's going down. I'm just going to divide, see what happens. 100 divided by 80. That is a change of down by 1.25. Let's check the next one. 1 to 2. I've got 80 to 64. 80 divided by 64. 1.25. So it is going to be the same change. So the data set can be modeled by an exponential function. Now let's look at graphing exponential functions. So here's the form of a function. A is greater than 0, B is greater than 1. They're called exponential growth functions. So remember, before we said A can't be 0, B can't be 0, has to be greater than 1, or can't be equal to 1. So when A is greater than 0 and B is greater than 1, we call that exponential growth. I would write that down. Exponential decay. A is greater than 0, but B is between 0 and 1. That's going to be decay. So also notice growth, when we read from left to right, it's going up. Decay, if we read from left to right, it's going down. Okay, it's a real easy way if they give you the graph to be able to tell. But sometimes they don't give you the graph and you have to look at the numbers. So let's look at some numbers. let's just look here, right? A is greater than 0. Check. B is greater than 1. Oh, look. Here's the graph. It is growth. It is going up. I already know it's growth because I could look at the graph. But what if they don't give me the graph? Okay? I did look at the numbers. But if they wanted me to graph it, the variable that I'm replacing x is the exponent. So I'm just going to plug them into this equation. So if I plug 0 in for x, well, 2 to the exponent of 0 is 1. 5 times 1 is 5. So I went 0, 5. There's the point. If I plug 1 in as the exponent, 2 to the exponent of 1 is still 2. So 5 times 2 is 10. So if I'm at 1, I should be going all the way up to 10. Ta-da! My graph doesn't go any further than that, so I'm not even going to do number 2. But it would be larger. Okay? If you notice here, it's growing. Sorry, I can't turn the page. There's a part B. We're going to try this one. Oh, look. A is greater than 0. B is between 0 and 1. So therefore, it is decay. It is going down. So this is decay. Okay, but now let's plug in is 1/2. So let's start with the easy ones. 0 makes this turn into 1. So 5 times 1 is 5. Yeah, I wrote 1. 5. So if I'm at 0, I should go up to 5. 0, 5. If I'm at 1, it's going to stay the same. So 5 to the 1/2 power, or 1/2 to the 1 power stays half. 5 times 1/2 is half of it. Half of 5 is 2.5. Now, put this in your calculator. Let me grab mine. I think I can do exponents on my phone. My other calculator's over there. There we go. Parenthesis 1 divided by 2 parenthesis squared. 0.25, and then I'm going to take that 0.25 and multiply it by 5. I get 1.25. 1.25. So 2 and 1.25. So 2, oh look, 1.25. So even those 3, I forgot to do this one. 1 is 2.5. Even those 3 shows me that it's going down, and I'd be able to make a graph. Okay, now you're going to try it. Graph each function and determine whether it represents growth or decay. Pause the video and do that now. Okay, so first I'm going to look here. Greater than 0, between 0 and 1, automatically tells me this is going to be exponential decay. Exponential decay. If I have to graph it, I'm going to use something easy. Remember, it's being replaced here, so I'm going to go 0. If I do 0, that's going to be, that turns into a 1, so 4. So from 0, I'm going to go up to 4. Now let me do 1. I'm plugging that in here. 1/2 to the 1 power is just 1/2. Half of 4 is 2. So at 1, I'm going up to 2. What if I do 2? 2 to the 1/2 power, or half to the 2 power, showed me that it was 0.25. So I'm going to do 0.25 times 4. If I can figure out how to use my calculator. 0.25 times 4 is 1. So at 2, I'm at 1. Notice we're getting a little bit of a curve. You could do more to find the actual curve. It's going to look something like that. Okay? There's a second check. Find out if it's exponential growth or decay. Greater than 0. Also greater than 0, but it's greater than 1. This is exponential growth. Exponential growth. They want me to graph it. Do the easy ones. Plug in 0, that's going to equal 1. 4 times 1 is 4. So 0, 4. Plug in 1. 2 to the first power is 2. 4 times 2 is 8. So from 1, I'm going to go up to 8. 2 might not fit on this graph. 2 times 2 is 4. 4 times 4 is 16. It's not even going to fit. It's going to be way up here somewhere. My graph is going to look something like that. Okay, that's it for today.